Well, hello again. This is the third part of the motors, and what we're going to do is we're going to talk about gears and things. Um, let's start by looking at this curve here. Now this is for a permanent magnet and type DC motor, and notice that this is the torque speed curve. You got torque and speed. And notice that the maximum torque you'll get is when you first start. This is before the motor starts to rotate. But if we have a load whose torque is less than this max, then it'll start. Now, if it's right at it, it may or may not start. But as long as it's below, then it may take a while, and the closer the torque of the load is to this max torque here, then the slower it's going to do. If the torque load is way down here, then it's going to start up really fast. Okay, accelerate. But what if the torque load is up here? Well, the torque load is higher than the torque produced by the motor, so the motor can't possibly produce a torque that will match it. So it'll just sit there, and it'll try to do as much as it can. It'll just sit there and get hot, and basically because you got a lot of current flowing, and eventually it'll probably burn out. Okay, so what we want to do in this lesson here is we want to go up to, let's see, is it this the one I want to do? No, I want to do this one. Okay, so what we're going to say is, well, let's do something with gears, right? And you've all seen this where you gear something down or gear it up or whatever. So let's assume the case that you got a motor and you got a little gear right here, and then you got a big gear that's hooked up to here, and basically this is hooked to a load. So maybe this has got like 10 teeth on it, and this has got 100 teeth or whatever. So we all know that if this little gear here is really small compared to this, then what's going to happen is that this is going to go a lot slower, right? Because if you got 10 teeth here, and each teeth meshes with a tooth in here, then basically this is going to turn fast and this is going to turn slow. Okay, so you might say, well, what's the advantage of that? Well, the big advantage is that if this is rotating really fast and this is rotating really slow, then the torque produced by here is going to be less than the torque going through here. So essentially what happens is, even though you're going slower, you got more torque. So you can actually turn this motor. If you took this motor, let's say that you took this motor and directly hooked, or this load, and you hooked it directly up to this motor, then it wouldn't turn because the torque of this motor, of this load, is much higher than the torque the motor can produce. So just sit there and get hot. But if you go through the gear ratio here, what will happen is the motor will turn its speed, but this right here will turn really slow, and it will produce the torque to turn it. So what you do here is you're actually multiplying the torque of the motor. Okay, so that's what we want to talk about now. Okay, so let's look at some basic drawings that I have up here. First, what I have is I have the wheel or the gear that's turning, and this, you could do this with pulleys or whatever. So I've got the gear right here, and so we got a radius called Rn, which corresponds to this, and then essentially, you have an angle through which it's rotating. If you want to know what the distance that it's rotated, if you know the angle in this, is all you have to do is multiply r times the angle. Okay, now the angle here is in radians. Okay, so you can't put degrees here. So if you take the radius and you multiply it by the angle in radians, then that will tell you the distance here that it is, okay, depending on what unit you have here, whether it's inches or meters or whatever. And if it's meters, that's a really big one, so let's just say millimeters or centimeters or inches. So, and the same thing for here, this bigger wheel is RL, okay, and of the load, and basically you have an angle that it's rotating through, And essentially what we have is RL times theta L equals the distance moved here. Now it should be obvious that the distance x that this is moving along here is going to be equal to this distance. Now if this is moving faster, which it is, then this is going to move through more rotations than this does. So if this goes through one rotation, that's probably only going to go through a portion of a rotation here. So xn and xl are going to be equal, okay? But what you're going to have is that the number of rotations here are going to be more for every rotation over here, okay? So let's look right here. So we got xn equals xl, which has to be because you get the same two spacing and stuff on here as you do here. So xn, the rotation along here, the distance is going to be the same distance as across there. And so you've got Rn times theta n, which is what xn is, and you got Rl times theta L is the distance. So we're just setting equal things to equal things. But notice what happens if we divide both sides by Rn. We see that the angle rotated by theta is going to be equal by theta n, which is the smaller wheel, is going to be RL over Rn times that. Since RL is the bigger wheel, that's going to be greater than 1. So the angle rotated by the smaller wheel is going to be bigger than the angle rotated by the larger gear or wheel. Okay? And what I do here is I go in and I define the ratio of the larger radius, which is the radius for the gear for the load, is going to be larger than the radius for the gear for the motor. And so I define that to be n, and so n is going to be greater than 1. And so this you can think of as like the mechanical advantage or whatever. So either you can say the radiuses, the ratio of the radiuses is n, or you can say the ratio of the angles here, theta n up here. And so the little wheel is going to go through a bigger angle than the bigger one, and the bigger wheel is going to have a larger radius, of course, than the smaller wheel or gear. So if I say wheel, I mean gear, so I don't have to keep saying that. Okay, so we've got kind of like a mechanical advantage, you might want to call it. Okay, now let's look over here. So we've got the smaller wheel is attached to the motor. The bigger wheel is hooked to the load. Okay, so we've got Vn, okay, or the velocity. This is the velocity of this wheel here, right? So Vn, and this is the tangential velocity of this gear or wheel, is equal to Rn times omega n, and V velocity of this equals RL times omega L. Well, here again, the angular velocity, okay, or not the angular velocity, but the tangential velocity has to be the same. So the speed at which this surface is moving and this surface is moving is the same, okay, according to this, which is obvious. So what I have is the input velocity equals the output velocity of an edge on here. So if you're riding on the edge of this, you're going to be going a linear velocity that's the same as this. Now that's different than the angular velocity, okay? The rotational velocity is different than the actual tangential velocity here. Okay, so if we start with this equation, plug it in, then we get another equation. And essentially what we get is that the angular velocity in radians per second is equal to n times the angular velocity of the big wheel, right? And so just summarizing here, what we see is that this is going through rotating faster than this is, okay? And we have the equations for both the angles. So theta n equals n times theta L, and we have omega n equals n times omega L. Now, work for rotational purposes is equal to the torque times the angle. Now, this is similar to when we're talking about work in rectilinear coordinates or linear things. We have force through a distance is work. Well, here is torque through an angle. Okay, and so here we can see that basically the torque in from the motor is equal to what? Theta in, theta of the motor gear over theta theta of the load gear over theta of the motor, and N times the torque of the load. Okay, or you can say torque in equals torque of the load divided by N. Okay, so or you could redo this to say torque of the load equals N times the torque of the N. And so as you can see, that what happens is the gear ratio actually multiplies the torque. So the torque appearing to the load is TL equals N times Tn. So we've multiplied torque by this situation. You can drive a heavier load because the torque is multiplied by N here for this motor. So the motor won't drive it directly, but through the gear ratio, you're multiplying the torque. Okay, let's see what else have we got here. So Tn equals TL over this, so on and so on. The other thing to consider too is the rotational inertia. So there's a certain rotational inertia that's involved with rotating this, and when we talk about inertia, we're talking about a resistance to an object being accelerated. Now in this case we're talking about rotational acceleration, and so basically we've got an inertia, rotational inertia, that's associated with that. And when we just looked at a slide that talked about the J's and everything like that, remember here so we talked about a cylinder and a ball, and basically here the rotational inertia is m times r squared over 2 or whatever. So now what we're talking about is we're talking about the rotational inertia of this load. And so as you can see, the actual rotational inertia seen by the motor now is this rotational inertia divided by N squared. Okay, so essentially the motor is not seeing the full rotational inertia of the load, is seeing that rotational inertia divided by N squared. Okay, now rewriting this equation, what the motor sees is that it's got the rotational inertia of itself, okay, and then you've got the rotational inertia of the load divided by N squared times acceleration equals the torque of the motor minus the torque of the load divided by N. Okay, so this motor has a chance of actually turning the load. Okay, and from the load view, essentially what we see is that the acceleration of the load is going to be the acceleration of the motor divided by N. Okay, so summarizing what we've done by having a gear ratio, a step-up type ratio, is we allow this motor to turn a much bigger load. And the reason we did it, because the gear ratio here increases the torque that's applied to the motor, it decreases the rotational inertia that the motor actually sees. And so the motor is turning fast, but the load is turning slow, but at least it's turning. Better to turn something slower than not to turn it at all, is what I like to say. Okay, let's go to the next. All right, so here what we've got is a schematic here. So here's a motor, here's some type of gear ratio or pulley or some type of device to transfer the torque to the load, and here's the load. And before, what we had was a little gear and the big gear. And so this is just an example. And so it says problem, given motor must rotate given load. Don't care about the speed of the load. Okay, so suppose that the torque of the load is greater than T max. Okay, then the motor will not rotate. There's just no way it can do. So the solution is you use a gear transmission. So here you basically go in and you choose the gear ratio in, so that the motor sees a torque which is equal to 1/2 of its max torque. Okay? And what we're trying to do is we're trying to match this load to the torque that the motor can generate. And what we'd like to do is have maximum power transfer, right? And we did this in the radio communications. Remember, we knew what maximum power transfer was. We went in and saw what the maximum available power from our source was, and we can do that with a motor. And so what we want to do is we want some kind of matching circuit, and there we had like T circuits or T networks and pi networks and LC networks to actually go in and match the load to the source so that we had maximum power transfer. Well, that's what we're trying to do here. So we choose the gear ratio in, so the motor sees a torque of this. Then the motor will rotate at a speed of W max over 2. And since the motor sees Tn over TL over N, we must satisfy this equation. So this is our gear ratio that we need. So remember, N is the ratio of the radius of the big wheel to the radius of the small wheel. Okay? And that's what we have here. We must make RL equals that, RL equals that. Okay? So let's go to the next one. And so here, actually, let's go back down. So was there another problem? Nope, that's it. Okay, and so here we go to this one. And so it goes through and continues with acceleration. This is the actual acceleration that we would see. And sometimes that's important. You don't want something to just go and just totally jump off its mounts because there's so much acceleration. But we could go in and calculate that using the equations now. The acceleration equals 1 over n times that. Okay, here's another problem. So given a load, we must find a motor to drive a load at the desired speed. Well, we got Tn equals TL over n, and we got this equals that. The rotational velocity or angular velocity equals that. We got power N equals this, TL times WL. And so what we do is we just choose a motor capable of delivering this power, and we adjust the applied voltage to get the omega L. Okay? Alright, now what I want to do is real quickly talk about some different types of load characteristics. For the most part, we've been talking about motor torque speed curves, but now let's look at different types of loads. And remember, the way you figure out the operating speed and the operating torque that the motor is producing is by going in and taking the characteristic for the motor, torque speed, and then taking the load torque speed characteristic for the load, superimposing them, and then where they intersect, that's the actual speed. So here what we have is different loads, and the first one is a calendar. Now calendars are like rollers, okay, and a sheet of paper may go between them or something. It may flatten something or extrude or whatever, but these are calendars. And so notice that here M corresponds to torque, and power is corresponds to the P. And so if we look at this curve here, that what we have is now we have the M, which is the torque, and P is the power. So, and then we have N is the speed. We see that for the calendars, that essentially the torque is linear with the speed. So as you increase the speed, the torque is proportional. Okay, so this is a proportional one. Now before, all we saw was a horizontal type torque, and we'll see that in a minute. But the load torque basically increases with the speed. So the faster you turn these rollers, then basically the actual torque load, or the torque required to drive it, is proportional or linear relationship to the speed. So some constant times that. Now the power, notice, is basically going to be a quadratic equation here. Okay. Now that should be, you should be able to see that, because remember, power equals torque times speed. Okay, and so if this is a linear equation, say some constant times n is the torque, and power is n times that, then it's going to be n squared. So that makes sense, right? So the power curve is increasing with speed. Okay, now let's go down to the fan. Let's do the fan next, because that's one we've seen. And so notice here that the characteristic of fans is that the torque is like a quadratic, right? And so m here, it looks like a quadratic. So it's a quadratic function. It's proportional to the square of the speed of the motor. Now here again, since the torque times the speed equals the power, you see that the power is going to have to be a cubic type function. Okay, and so this is for pumps and fans and centrifuges and mixers. Now let's go to a different type. So this is something where you have like a hoisting gear, a conveyor belt, or something like that. And notice that once it starts, then basically the torque is constant. All right, so it's a constant torque load. Okay, and so this is the example. The other example that we're using in our equations is we had the torque speed for the actual motor, and here this is an example, a hoisting gear. Okay, something lifting up an engine, or like an elevator or conveyor belt or something like that. So this is basically a constant thing. And so since this is constant with speed, then to get the power, you multiply the speed times that. So this is going to be linear. So it's the torque times the speed is equal to the power. Okay. Okay. So let's go to a winding machine drill. Okay. Now here, the torque is like equal to what? 1 over the speed. It looks like 1 over x. Doesn't this look like 1 over x from your algebra class? Okay. Okay, and so our 1 over the speed. Okay, so if the torque is proportional to 1 over the speed, then if you multiply that by the speed, then the ends cancel out and it becomes constant. So this is a constant power type machine. Okay, and so winders, fencing, facing latches, rotary cutting machines, these are constant power and 1 over speed type torques. Okay, so there you go. There's some various types of loads that we'd use, and you should now see that once you know the torque, you just multiply that times the speed, and that will give you the power. Okay, all right, let's see what we got going on next. Okay, this is advertisement for some DC tester machine. Actually goes and makes some measurements and stuff, and we have some torque, and here they're using M for torque. So here's a torque speed here, torque speed there. So I don't really care about that. I shouldn't have included that one in, but hey, what the heck. And then here is basically talking about AC machines, and we haven't talked about AC machines. We're going to do that next. But notice that the torque speed curve is quite different. Okay, so anyway, this concludes part 3, and so now we have 3 parts, and have fun.